This video covers the mention pair architecture for coreference resolution. I'll provide an overview of the architecture and then work through a case example. After that, I'll go over additional details about learning probabilities and making predictions using this model, before closing with some advantages and limitations of the approach. The underlying premise of the mention pair architecture is simple. Given the pair of mentions, where one mention is a candidate antecedent and the other mention is a candidate anaphor, the model seeks to determine whether or not the two mentions co-refer. It does this by computing a probability indicating the likelihood of the two expressions to co-refer. The approach does this for every plausible pair of candidate anaphors and antecedents, with an end goal of learning to predict high probabilities for pairs that actually co-refer and low probabilities for pairs that do not. For example, if we go back to our sample text from the previous video discussing coreference tasks, let's say we've identified all of the entities that are circled. For each of these entities, we're going to want to compute the probability that the entity co-refers with each of the other entities. So, for example, with the entity University of Illinois at Chicago, we'd want to compute the probability that it co-refers with natural language processing, UIC, faculty, and so forth. We would hopefully predict high probabilities that UIC, the school, and it co-refer with University of Illinois at Chicago, and low probabilities that natural language processing, NLP, and Natalie Party do. Assuming that those entities surpassed some internal threshold, we would go ahead and resolve them as all referring to the entity representing the University of Illinois at Chicago. That provides an overview of how the architecture works in general, but we still need to fill in the details regarding, for example, how these probabilities are actually learned. Learning probabilities in the mention pair architecture is pretty straightforward and is performed in the same way probabilities are learned in other machine learning architectures. Given a labeled training set with labels indicating antecedent-anaphor relationships, we can take as a positive sample the actual labeled pair between the anaphor M sub j and the antecedent M sub I. We can take as negative samples all of the pairs between M sub I and M sub k, where M sub k is a word existing between M sub j and M sub I in the training set. So we have many more negative samples than positive samples. For each sample, we extract some array of features. So these could be manually engineered features or implicitly learned representations like word embeddings or even a combination. Then we train a classification model to distinguish between the positive and negative samples. To make predictions then, we can take our trained classifier and apply it to each test instance. Typically this is done in one of two clustering paradigms, known as closest first clustering and best first clustering. In closest first clustering for a given possible anaphor, we make predictions for each prior mention and then take the first mention with a probability greater than some threshold. Typically this will be 0.5 as the antecedent for that anaphor. In best first clustering for a given possible anaphor, we make predictions for each prior mention and then take the mention with the highest predicted probability as the antecedent for the anaphor. There are both advantages and disadvantages to the mention pair architecture. An advantage is that it is quite simple to implement, making it a nice baseline. Two disadvantages, however, are that it doesn't have any mechanism for directly comparing candidate antecedents with one another, so it can't determine what the best overall antecedent for an entity would be. And building off of that, it considers only local pairs of entity mentions, so it isn't able to consider contextual cues that may be useful from other mentions of the same entity. One way to address the limitations just noted is to implement an alternate formulation referred to as the mention rank architecture, which directly compares antecedents with one another to choose the highest scoring antecedent for each given anaphor. It does this by computing a softmax function, so essentially a probability distribution over all possible antecedents. Training the mention rank architecture is a bit trickier than training the mention pair architecture because in existing coreference datasets, we don't have labels indicating the best antecedent from among a set of possible antecedents. This issue is typically addressed just using simple heuristics to determine the best antecedent for a given anaphor, for example, by assuming that the closest antecedent to the anaphor is the best. More sophisticated machine learning techniques can also be used for this. Just like with the mention pair architecture, mention rank models can be trained using manually engineered features, neural features, or some combination of the two.